we will start module 5 of this course. In this module, I will be talking about second order differential equations and the ways to solve them. Now, second order differential equations are almost ubiquitous in all of physical chemistry. So, for example, in quantum mechanics, the Schrodinger equation, the time independent Schrodinger equation is typically expressed as a second order differential equation. You have other equations like the diffusion equation in which is used in non-equilibrium transport phenomena, and which is also written as a second order differential equation. And there are various equations that you see in various parts of physical chemistry that involve second order differential equations. So, without wasting much time, let me get to the topic of today's lecture. That is, in today's lecture we will be talking about homogeneous second order ODEs and basis functions. So, what is a homogeneous second order ODE? So, what does it look like? So essentially, if you have a second order ODE, you have to have a something like d square y by dx square. Okay, I am assuming x is the independent variable and y is the dependent variable. So, you have to have a term like this, okay. And let us take first degree equations. For convenience, we will just take first degree equations. Okay, so, d square y by dx square has power 1. Okay. Now, if you had a homogeneous second order ODE, then each term will have y or its powers, y or any of its derivatives to the same power. So, for example, if you have d square y by dx square, then you could have a term that has dy by dx times some function of x. Then you could have something like g of x times y, okay, some another function of x times y, okay. And then so if you did not have anything else, okay, so this is you would just set this equal to 0. So, this would be a general homogeneous first degree second order ODE. So, homogeneous, each term contains either y or a derivative of y or a second derivative of y, okay, but to the same, but there is no power of it. So, and you do not have any cross terms, okay. So, therefore, this is a homogeneous first degree second order ODE. Now, we mentioned something in the last class about homogeneous differential equations. This is the following. Suppose you have a solution y, so given two solutions y1 of x and y2 of x, okay, we can construct other solutions by linear combinations. So, I will just call it y h, okay, h stands for homogeneous. This is C1 y1 of x, this is a function of x, plus C2 y2 of x, and you can choose C1 and C2 arbitrarily. So, for arbitrary C1 and C2. Okay. So, anytime you have two solutions, any linear combination of solutions will also be a solution. You can easily verify this by putting it in the differential equation, and you will realize that in order for this to be true, each term should have y or its derivatives to the same power. Okay. You can easily substitute this and verify that this is true. So, now suppose y1 of x and y2 of x are linearly independent. And what I mean by linearly independent, what we think of as linearly independent vectors in vector space of function. Okay, now again I would like you to recall what we learnt in when we were learning vectors. We said that we can generalize the idea of vectors to functions. We can think of functions as vectors in a vector space involving all functions. Okay. Now, in that vector space of all functions, if y1 and x and y2 are x are linearly independent. Okay. And now, what does it mean by linearly independent functions? So linear independence implies y1 of x is not proportional to y2 of x. That means, I cannot write y1 of x as y2 of x into some constant. Okay. So, if these two functions are linearly independent, okay, then any solution, and this is any solution can be expressed as y h of x is equal to C1 y1 of x plus C2 y2 of x. Here C1 and C2 are chosen, C1 and C2 are suitably chosen. Okay. So, you can write any solution as a linear combination of these two solutions. Okay. This is like writing any arbitrary vector in 3D space as a linear combination of the unit vectors I, j and k. Okay. So, just like that you are writing any solution of this differential equation as a linear combination of these solutions. Okay. Now in this case y1 of x and y2 of x are basis functions. Basis functions in now this is these are basis functions in not the space of all functions, okay, but in the space of solutions to the second order ODE. Okay, this is a very interesting concept, that what we think of is that you take all possible solutions of the second order homogeneous differential equation. They form a vector space, and if y1 and y2 you take any two independent linearly independent vectors, they can be treated as a basis for that space of solutions. Okay. So in order for y1 of x and y2 of x to be a basis, of course it should be that necessarily y1 of x not equal to 0 and y2 of x not equal to 0. So these two should not be equal to 0, because 0 is also a solution of this homogeneous differential equation. So you can say that y equal to 0 satisfies this homogeneous differential equation. So it is necessary that when you are writing this you should have y1 of x, and the non trivial solution is y1 of x not equal to 0, y2 of x not equal to 0. Okay. And then you can, if you can express any arbitrary solution as a linear combination of these solutions, then you can think of y1 of x and y2 of x as basis functions in the space of solutions. Okay. Now notice that a few things about vector spaces. So set of all functions of x, this is a vector space of functions. Okay. Now the set of all solutions of homogeneous So, just to emphasize, it is first degree homogeneous second order ODE. Okay, this is what we talked about, set of all solutions of the first degree homogeneous second order ODE. Okay. These are also functions of x, these are also functions of x. Now, what we are doing is, this forms the vector space of solutions to the differential equations. So, these are the functions that satisfy the differential equation. Okay. So, what you can see is that this is a subspace of the space of all functions. Okay. So, the vector space of all functions will contain the vector space of all the solutions. Okay. Now, why is this a vector space? Because you take any linear combination of two solutions, you will get another solution. Okay. So, therefore, the set of all solutions is a vector space, 0 is a solution. Okay. If you have f of x, if you have y 1 of x is a solution, then minus y 1 of x is also a solution, and so on. Okay. So, you have a vector space of all solutions to the second order homogeneous differential equation. And so now what this means is that that if you have a so the goal of solving second order homogeneous ODE is reduced to finding basis solutions, basis functions. So, what you are supposed to do is to find these basis functions, find two linearly independent solutions, that is two linearly independent solutions. So, if you can find two linearly independent solutions, you are done, because general solution can be written as a linear combination of these two solutions. So, you can write a general solution in this form. So, this is what we call the general solution, where C1 and C2 are the arbitrary constants. Okay. So, if you know y 1 of x and y 2 of x, these are two linearly independent solutions, then you can write the general solution as a linear combination of these two. Okay. So, now you can so the goal is to find these two basis functions. So now we look at different cases. So, the first case, okay, y 1 of x is known, need to determine y 2 of x. Okay. So, you need to determine y 2 of x. Now, so how will you go about doing this? Okay. Now, there is a method called this method is called variation of parameters. Okay. So, according to this method, okay, what you will say is try y 2 of x equal to r of x times y 1 of x. Okay. Remember, y 2 r of x cannot be a constant. Okay. It cannot be a constant, because if it is a constant, then y 2 of x is proportional to y 1 of x, and the solutions are not linearly independent. Okay. Now if you try this, okay, so okay, let us start, let us take the differential equation, and I will just go back to our original differential equation, which had this form: second derivative of y plus f of x times dy by dx plus g of x times y equal to 0. So I will just write it in very compact notation: d square by dx square plus f times dy by dx plus g y equal to 0. Okay. Now, alternate notation, I will just write this notation here. Okay. which you will find very common. So, instead of writing the second derivative, you just write it as y double prime plus f y prime plus g y equal to 0. So, I will be using both these notations during this course. Okay. So, this is compact notation, and you will also find it often used in various books. Okay. Now let us say, so now substitute y 2 equal to r y 1. Okay. Then what you get is that y 2 prime equal to r y 1 prime plus r prime y 1, y 2 double prime equal to r y 1 double prime plus r double prime y 1 plus 2 r prime y 1 prime. Okay, you can easily work out these things. Now you take this and substitute in the differential equation. So when you substitute in the differential equation, I will be using the compact notation. So for y 2 double prime has to satisfy this differential equation. So if I substitute this here, what I will get is r y 1 double prime plus r double prime y 1 plus 2 r prime y 1 prime. Okay, that is the first term. Then I have plus f r y 1 prime plus f r prime y 1 plus g r y 1 equal to 0. Okay. Now if you take the terms that are proportional to r, okay, not derivative of r, just r, okay, then what you get is r times y 1 double prime plus f y 1 prime plus g y 1. Okay, those are the terms that are proportional to r. Okay. Then the remaining terms look like r double prime y 1 plus 2 r prime y 1 prime plus f r prime y 1 prime equal to 0. Okay. Now what you notice is that this term that we were this term that is proportional to r. Okay, so this is y 1 double prime plus f y 1 prime plus g y 1. Now since y 1 satisfies the differential equation, so this term is equal to 0. Okay. So now and the remaining terms I can write as r double prime y 1 plus r prime 2 y 1 prime plus f y 1 prime equal to 0. Okay. Now you notice that there is no term involving r. So this is just so if I call r prime equal to u, okay, r double prime equal to u prime. Okay. Now you can straight away see that this is just a first order differential equation in u. So you have u prime y 1 plus u 2 y 1 prime plus f y 1 prime equal to 0. Remember, f is a function of x. Okay. So then I can immediately solve for u. So u prime by u is equal to 2 y 1 prime plus f y 1 prime divided by y 1. So solving you can get can solve for u. Okay. And once you have solved for u, okay, then you can do from u you can solve for r and y 2 is equal to r y 1. Okay. So essentially what we are saying is that this the important message is that variation of parameters can be used to obtain second linearly independent solution when one solution is known. Okay. Incidentally, I mean you can just to say a little bit about this, when you integrate this you will get ln of u is equal to integral. Okay. Now, you get 2 y 1 prime by y 1. So, that is twice ln y 1 plus now we will get integral f y 1 prime by y 1 dx. Okay. So, that is what it will look like. Okay. So, this is what this integral will look like. Okay. Now, if you exponentiate everything, then you will get u equal to e to the y 1 square and so on times this term. Okay. So, I mean we will see we will work out some of these examples and then we will see how this works in practice. But essentially what we have seen through this is that if you know one solution you can get the second solution. So, if you know y 1 you can get y 2, and once you know them you know the general solution. So, the problem is solved. Okay. So, now there are a few other things. Okay. So, at least there are still some concerns. Okay. That is, how do you determine the first solution? Okay. So, how do you determine the first solution? Sometimes just by luck or by inspection you can get the first solution. Okay. But a more formal method to get the first solution would be the power series method. Okay. Now, so this is one thing that we will be discussing a little later. Now, the other case that we will be discussing soon is what to do if your equation is not homogeneous. Okay. So, that is the second case that I will take up in the following lecture. So, I will conclude this lecture here. So, in the following lecture we will take up the second case in which the equation is not homogeneous. Thank you.